When looking at arithmetic sequences, we noted that the sum of an infinite arithmetic series would not converge. However, if we look at geometric series, we can note that if r is less than 1, the infinite geometric series does converge, and the formula or the sum of that series can be calculated using this. We can use that sigma notation beginning at 0 up to infinity and write that series in the same form. Think about it in terms of if you continually divided something in half and added up all of those values, it would converge to a value. It would not keep getting bigger because you're adding less and less each time. So as long as that common ratio is reducing the values as you go down the sequence, this series can converge. So let's look at an example. If we have this first infinite series here, the sum from 1 to infinity of 5 times negative 1/2 to the n minus 1, first we have to identify the values a1 and r. So when I plug in n minus 1, I get that a sub 1 is 5. And I get that because I do 5 times negative 1/2 to the 1 minus 1. Notice this becomes to the 0 power, which is just 1. So my a sub 1 is going to be 5. From the summation formula, we know that the r value is negative 1/2. So plugging this into our formula and noting that r is less than 1, or the absolute value is less than 1, we can apply the following formula. S is going to equal a sub 1 over 1 minus r. A sub 1 was 5. We have 1 minus a negative 1/2, which results in 5 over 3/2, or 10/3. It's going to converge to 10/3. Let's look at the second example here. Note how this series is actually written. The formula S equals a sub 1 over 1 minus r applies directly to two forms of the summation. So in other words, we can use this summation from n equals 1 to infinity for a sub 1 r to the n minus 1, or we can use it in terms of from n equals 0 to infinity a sub 1 to r to the n. In this case, the form doesn't match quite either one of these. So we need to write out the first few terms to identify the first term in the series and the common ratio. So if I write out when n is 1, I get 3 times 1/10, so I get 3/10. When n is 2, I get 3 over 100. When n is 3, I get 3 over 10 over 1,000, and so on. From this, we can see that a sub 1 is actually 3/10. So be careful how these are written. And we can also see that r is going to be 1/10. Now we can apply this to the formula where we have a sub 1 is 3/10 over 1 minus 1/10, which results in 3/10 over 9/10, or 1/3. This example notes the important relationship between geometric series and that decimal representation. Notice that we've shown that sum is approaching 0.333. And similarly, other decimals, we can note that repeating decimals actually do converge to a value.